Hi, my name is Uchechukwu Ngozi Mwachukwu from Cardiff Metropolitan University, Wales, United Kingdom. This research paper, with recognition in system field using computer vision algorithms, was done as my dissertation in fulfillment of my master's degree in data science. The presentation overview is going to be in 6 sections. The first being the introduction, research purpose, background and related work, methodology, results and evaluations, and conclusions. Introduction. Agriculture has proven to be one of the sectors that contribute hugely to Nigeria's GDP and is also a solution to the ever-growing population of the world at large, because daily the world's population is growing and there is need to have it sustained and developed, and agriculture stands a chance. But the agricultural sector has its own challenges. For example, weeding in farming has posed a serious challenge to the crop yield actualized and also to the environment, because you can get environmental pollution from the herbicides and all that is being applied. And this affects not just the small scale farming, also the large scale farming. Now, when you come to the choice of plants that was used for this paper, that is sesame crop, it is one of the marketable crops in agriculture, owing to its numerous uses in food production. That is, it has a great value of money, it is lucrative. But most farmers that are into system farming, they do encounter the challenge of poor yield because of the weeding, and this can be attributed to the weeding control measures that are being employed. For instance, they have the challenge of lack of funds. Some farmers, they may not be able to afford the labor cost associated with manual weeding, and by the time it's realized, maybe they've planted and the planting processes are going on. When it gets to the time for weeding, they might not afford the money to pay for this. And before you know what's happening, the weed has grown at same length with the crops. And thereby, they begin to compete with the nutrients that are available for the system crops. And this has already started affecting the production of the system. Some even tend to use hand picking. Imagine using hand to pick like 5 hectares. You could do that for a small area of land, but when you begin to pick a large area, that takes a lot of time. It is tedious, and it also poses health challenges. And it's not even ideal for large scale farming because you won't be able to actualize much from it. Then again, methods such as mechanical chemicals, they use maybe through the use of herbicides. It not only causes environmental pollution, it affects the plant as well. Because the target is an area of land, you're trying to spray the herbicides in the large area and trying to kill the weed. But at the end of the day, those herbicides end up killing the plants as well. Because there are little or even the similarity between the plants and the weed are much. So you have little to differentiate the weed from the plant. But with the advancement in technology, digital automation of agricultural processes, it has helped to tackle these challenges though. But regions such as Nigeria, they still adopt old practices. Well, methods such as CAFNet, site-specific weed management, CNN, are applied in weeding. That is why this paper, in addition to applying CNN, will also utilize bounding box techniques for a better classification of image position to be able to identify where the weeds are located and target the weeds. And this will give a better classification of the image, and also it gives it edge in the image classification and for a better sustainable environment. Because if these weeds are known, this is the position, this is where the image is located, and that is weed and this is plant, you can be able to just focus on target on the weed, get it off, and then you leave the plant. For the research purpose, it is to create a machine learning algorithm that will be able to determine plant species from images and distinguish between weeds and crops in a system farm with a view to achieving an improved yield. At the end, this paper tends to answer these questions. 1. To what extent does the application of CNN in weeding improve the expected yield in crop farming? How effectively can CNN classify, detect, and segment plant species? And the last being, to what extent are features considered in achieving an efficient result in plant recognition processes? Background and related work. Previous papers on related subjects were reviewed prior to this paper, and it was gathered that computer vision leverages on image acquisition, processing, classification, feature extraction, and description, and it also uses neural network with many layers. And the second being, there is precision weeding, and this contributes to greater farm yield because there is a clear difference between the crop and plant, and when this is established, then it is easier to target just the weeds than targeting the whole farmland, whereby random spray is being done in an area of land and is expected to just target the weeds. At the end of the day, both the plant and the weed is affected. Thereby, there's going to be a reduction in yield. These are the methodology employed to carry out this research. We have the architecture of the model, data preparation, scaling the data frame and visualization, splitting data, data pre-processing, building model using TensorFlow and Kansas, model compiling, and model training. So this is the pictorial view of the architecture of the model that will be used in this paper. TensorFlow and bounding box was used as the convolutional neural network model that will be detecting the objects in images, because some of the images from the Sesame farm used in this paper, it has more than one plant enclosed in an image. So some of the images now, although some has plants, some are weed, but some of the images have both plant and weed at the same time. So it will be difficult for the image classifier to detect the individual object. So this is why the paper is using a CNN, so that it will be easier for you to detect the objects and also be able to classify it. And if you recall, the research problems which we are aimed at how effectively CNN can detect and classify weeds and crops, and what features can be considered while locating the object. In solving this problem, the image classifier, which is the CNN, that has two neurons as outputs, was used. And this gave out outputs representing the probability of the dataset. And the probability is either weed or plant. And then the class that has the highest probability, which is the softmax function, was applied at the output layer, which will enable it to classify and distinguish this is plant and then this is weed. In solving the second problem, the object was located by having a bounding box being drawn on it, which means that the neural network utilized the pixel coordinates of the top left corner and bottom right corner of the object of the bounding box. And this made the design of the convolutional neural network to have 4 neurons at the output layer. It has the x minimum, y minimum, x maximum, and y maximum. So these two designs of the neural network with different output layers were merged so as to have a single neural network with 2 branch outputs, because it will be difficult and cumbersome for the dense layers of the neural network to be fully trained if it runs the different neural networks simultaneously. So to make it easier for the machine learning model to learn and also to easily spread the data across layers effectively, the size of the plant image, which also serves as the input feed, was rescaled. It starts by measuring at 512 pixels by 512, and then it's being reduced to 256. And this continued throughout the layers on the neural network. So to achieve this merging into a single neural network, the CNN layers was made common and shareable. Hence, the extraction of the features in solving both research problems, and this will be carried out equally. And then after that, the two outputs were branched with different dense and output layers so that they can achieve different outcomes. To prepare the dataset was publicly sourced from Kaggle, and the dataset had about 1,300 plant images that comprises of both the sesame crop and weeds with their corresponding yellow format label. And this yellow format label served as image annotation for the bounding boxes because it helped to mark the vision. The images were of varying sizes and captured at different background and different growth stages. And this proved helpful when the model was being trained because it gave an efficient result. So the dataset was now divided into train, test, and validation dataset. Now, for the scaling of the dataset, looking at the image, it further explained the positioning of the objects in the images using bounding box. And being that the data frame has its coordinate labels in decimal, the x center and the y center parameters had to be converted to integers so as to correspond with the pixel value. This was done by multiplying each coordinate, the coordinate value, by 512, which serves as the width and height of the images. And then using the formula by the right hand side, the new parameters, the x minimum, x maximum, y minimum, and y maximum were derived, which help with the building of the data frame. Now, visualizing the data set to identify the patterns and the trends, and also to get a better understanding of the positioning and location of the images with their coordinates. These two plots, the joints and the scattered plots, was created. Now looking at the plots, the joint plot analyzed the relationship between the two variables x and y. And looking at the scattered plots, there appears to be a positive relationship between the x center and y center. And this shows a strong correlation between both variables, that is the x and y variables, as most of the images have their coordinates located at the middle, which makes it better when the data is trained. Now, the plot also showed a marginal plot positioned horizontally, which shows the distribution of the x-independent variable, having its value concentrating at the middle, and same as the marginal plot positioned vertically, showing the distribution of the y-independent variable. The distribution plot shows the conformance of the joint plots, and the class plot shows the value of the plants are not imbalanced, as the image class is made up of about 700 plants and 600 weed, which appears to be a right proportion for training machine learning model. And when you look at the plot, it also shows that the x center and the y center shows the most values of the images are located at the center, and the w and the h plot, that is the width and the height, the plot depicts the variant sizes of the image of the plant. This image shows the cross-section of some of the images from the data set, which comprises of the weed and crop at different growth stages. And looking at each image, it has a dimension of 512 by 512 by 3 pixels, which represents the width, the height, and the channel. Now for the model compiling and training, hence the two branches designed for the output has their own designated function. The first being for classification of the plant classes, and the second being for bounding box predictions. Appropriate loss function was set up for each function by using the following. Number 1, for the localizer head, mean squared error loss function was used, and for the classification head, sparse categorically cross entropy loss function was used. So with this loss function, the Adam optimizer and the matrix accuracy, the model was compiled, because having the loss function gives signal to the model training when deciding if the training is to be continued or not, and this served as a measurement on how good the model was when making predictions. We know that the Adam optimizer is the approach at which the gradient is using to descend in the loss function with respect to the input, and it was also applied in the model compilation. So the gradient descended and was used to check the output loss changes. It was also used to check the weights and the biases. So when the change appeared to be high, the Adam optimizer will minimize it, and when it appeared to be low, it will also minimize it until the change and the training stops. So now the accuracy matrix was used to monitor the model progress, and for the model to be trained, 30 epochs and the batch size of 60 was used, and 2 target labels were also defined. These 2 target labels are the train and the validation target, such that the validation target was used to check if the model was performing well when it was being trained, because early stopping had to be applied to also check. For instance, when the model training is going bad, the target does this by noting the performance of the validation loss against the training loss, and it saves the best model at every point this occurs. So it's keeping a check on it. When it has the best model at every point in time before the error occurs, it saves the best model. And for the choice of batch size of 60, it's such that the model is picking 60 images at a time while extracting the weights and the features before going on to pick the next. This was because doing it this way, it makes the model training to be more efficient compared to selecting all the images in the data set at once. So if it's going by 60 batches and dealing with 60 sizes at the same time, like at every point in time, it's choosing an image, extracting the image, checking the patterns, checking everything that has to do with that image, it makes it better than when it's selecting it at once. Results and evaluations. Now, going to the training history on validation and the test data. While training the data set, it was observed that validation loss improved by 0.78 to 0.74, same as the accuracy, which improved from 0.59 to 0.63. For bounding box, it improved from 0.48 to 0.50 for classification. This cycle of training and validation was completed for the defined 30 epoch, and the following result was obtained. For loss, it had 0.71, classification accuracy is 97.7%, and the bounding box accuracy was 0.79, that's 79.5%. For the trend history performance, going to the trend history of the validation and bounding box loss, the general trend of the graph shows that the bounding box loss and the validation loss were all decreasing at the same time, which shows that the model did not overfit, making it able for the model to achieve a better result on the test data. Then the trend history of validation and the class loss. This shows the relationship between the class loss and the validation loss. It was observed that the model maintained a good fitting because the general trend decreased uniformly. The graph also shows the classification training and bounding box training accuracy. It will be seen that there exists a good learning. The good learning rates as the accuracy increased and got better with time. Evaluating model on test data. The test data making, which is 216 images, that's 20% of the original data set, was brought in for the model to evaluate after testing. The following results was achieved. The loss 0.71, classification accuracy 0.86, that's 86.5%, bounding box accuracy 72.6, which is 72.69%. And the accuracy results obtained shows that the model performed almost at the same range with the train results. To cross-check with the data, the performance of the model was checked, and the following images were obtained, which showed the model is making 99% prediction for both the crop and the weed. So to further have an insight into the predictions and analysis of the obtained results, classification reports, confusion matrix, and ROC curve were carried out. So using the confusion matrix and taking positive as crop and negative as weed, the following results were obtained. True positive 99, false negative 17, false positive 24, true negative 120. This shows that out of 116 crops that were in the test data, 99 of them were correctly classified as crop, while 17 of the crops were misclassified as weed. Then out of 144 weed in the test data, 120 classified as weed, 24 misclassified as crop. Because the classification report is a performance metric, and it was used to check the precision, recall, the F1 score, and support of the classification trend model. Looking at the table, it shows that out of 260 data used in testing, 116 was well predicted as crop and 144 was well predicted as weed, which calculated to give the final accuracy of 84%. And this is supported by other classification parameters in this report. So the last one being the ROC curve, it showed the trade-off between the true positive rate, that is the sensitivity, and the 1 minus false positive rate, that is the specificity. So the true positive rate shows the proportion of the positive predictions that was classified correctly, while the false positive rate shows the proportion of the negative prediction that was correctly classified. So the graph shows that the curve lies between the 50-50 probability line, covering an area under curve of 84. Recommendation. This study of plant classification is a time-consuming project due to the time and process involved. And in the case of this research, time was a limitation. Hence, it was limited to developing only 2 models, being the Keras and TensorFlow and bounding box. In the future, this research will focus on comparing with other algorithms to ascertain their performance, and to also implement the algorithms in a robot for farm weeding, thereby seeing its physical applicability and seeing if it works effectively. Finally, the conclusion. This paper, which focused on developing a CNN machine learning model that could classify weed from sesame plant, explored Keras/TensorFlow and the bounding box model, and then utilized 1,300 images from a sesame farm and served as an input in the 2 branched output neural network, which rescaled the images, extracted the features, and then classified and localized the output, giving a result of classification accuracy of 86.5% and bounding box accuracy of 72.69%. According to the results, the model showed low overfitting and low underfitting, and with a good learning rate, making the proposed approach to show a satisfactory performance. Thank you.